Okay, welcome to Note Set 21, where now we really will finish Chapter 4. I lied in the last video. I said I thought that was the last section of Chapter 4, but it's not. We've got one more, and this is on things called orthogonal bases and Gramschmidt, and one other thing that probably should be noted here but isn't in the title. Something called the QR decomposition, which is pretty important decomposition for a lot of signal processing things, and probably other areas too. So my area is signal processing, so I can tell you precisely where all these things are used in that field, and I have a somewhat of an idea of where things are used in communications and controls, and then outside of those areas, I can guess where a lot of these things are used. I know they are used in those other areas, but I have less precise knowledge of exactly where these things are used. Anyway, these things are used in all sorts of places. So here's what we're trying to accomplish in this particular note set. Well, we want to see how orthogonality makes it easy to do the projection. So in the context of a projection, remember there were three things. There's the little p is the actual projection itself. The big P is the projection matrix. And x hat is the kind of the coefficients of the vectors that we are using that form the subspace of the that we're projecting onto. So when the vectors that span the space that we're projecting onto are orthogonal, the formulas for these things become easy, and that's really not the point of this. Not that the formulas become easy and therefore it's easier for us to remember them. They become easy, and it's therefore easier for a computer to compute them. And so why would you care about how easy it is for a computer to compute them? Well, these days, even though computers are really fast, we're asking them to do lots and lots and lots of things all at the same time. And I'm not talking about while you're doing word processing and searching the web. I'm talking about embedded computers that are inside radar systems or cell phones or whatever that are being used to implement very advanced algorithms for signal processing or communications, or algorithms inside control systems that are helping an airplane fly. And I'm sure, like I said, in other areas there are things that these things are needed for. But we want to be able to do any of our real-time computations as fast as possible, because that allows us to make the algorithms more complicated. So we want to see what orthogonality does for us, and then since it appears to be useful, we would like to figure out, if we're given vectors that are not orthogonal, how can we get ourselves into an equivalent set of vectors that span the same subspace but are now orthogonal so that we can take advantage of this nice property. So we've already talked about orthogonal vectors and the concept of orthogonality and the term orthonormal. So we're just reiterating that here, and this book reserves the symbols Q whenever possible to talk about orthogonal or orthonormal vectors. They won't. Obviously we can't always use the same symbols. If we have two different sets of orthonormal vectors, we might have to call them different things or resort to hats and tildes and things like that. Anyway, the point of an orthonormal vector, a set of vectors, is that every pair, so this is for every ij, so 1 and 2, 1 and 3, 1 and 4, so on, 3 and 4, 3 and n, every pair of two different ones, that's when we say I is not equal to j, this inner product is equal to 0. So that's the orthogonality. And when I and j are equal to each other, that means we're doing the inner product of the same vector with itself. So we might be doing 1 with 1, 2 with 2, 3 with 3. And when we do an inner product with itself, what we're really computing is the norm squared. And so to be orthonormal, that norm squared has to be equal to 1. And if the norm squared is equal to 1, then the norm itself is equal to 1. So orthonormal means we have orthogonal vectors that also have unit length. So if we have a matrix that has orthonormal columns, not only do we use the little q's to talk about the vectors, but if those little q vectors form the columns of some matrix, we'll try to reserve a special letter, capital Q, for that matrix. And this is just showing what happens when we form such an orthonormal or orthogonal matrix with orthonormal columns. The Q transpose times Q gives us the identity matrix, and you can see why that is. When we do Q transpose times Q, what we're doing is each element over here is the inner product between one row and one column. So the things down the diagonal are something with itself. So Q1 with Q1, Q2 with Q2, anything off the diagonal. So let's say this 1, 2 element here would be Q1 inner product with Q2. Well, those are orthogonal to each other, so those all go to 0. So everything off the diagonal up here and everything off the diagonal down here, those are all zeros. So we didn't really quite fill in all the zeros here, but we tell you that it's I, so you know what it looks like. And then down the diagonal we get 1s because these are orthonormal columns. So down the diagonal we get the norms of each vector, actually norm squared of each vector, and since they've been normalized to unit vectors, we have norm of 1. So so far we haven't restricted these Q matrices to be square, but if it is square, then we can see that this condition, which holds regardless whether it's square or not, but square and orthonormal columns, this means that Q transpose is equal to the inverse of Q. So if we have a square Q and all the columns are orthonormal, we know that it has full rank, we know that it will be invertible, and this just establishes that Q transpose is the inverse of Q. And in that case, we call Q an orthogonal matrix. So technically, to be an orthogonal matrix, it needs to be square with orthonormal columns. So it's always bugged me that you need orthonormal columns to be an orthogonal matrix. I really wish that they would have just called that an orthonormal matrix, but sadly they didn't, and it got ingrained and it stuck. So that's what we're stuck with. So we'll look at some examples of these orthogonal matrices. Here's one called a rotation matrix. So if we form a 2 by 2 matrix for any value of theta, so we get to choose the theta here, and so you pick whatever theta you want, you evaluate cosine at that theta and put it down the diagonal. Evaluate sine of theta and put sine of theta here and negative sine of theta here, and that matrix will now, when you apply it to any vector in R2, will rotate that vector by the angle theta that you chose to compute there. So and we can also verify that this is an orthogonal matrix by just forming Q transpose Q. So Q transpose, something seems wrong here. I'm going to have to check this, see, because this is, if this is Q Q transpose needs to have the negative sign down here, so I'm going to have to check that to see, to make sure that we have it right. My hunch is that this is wrong up here, that this should be negative down here. That's my hunch, but maybe not. I'll have to check that, and I'll fix it in the actual notes. But however it turns out, you can check this. You'll get things that will be like, it looks like this actually works the way that we have it down here. So for the first element here, we would have cosine times cosine plus negative sine times negative sine. So this first element, the 1, 1 of the result, would be cos squared plus sine squared, and that's a famous trig identity, is equal to 1. Then we look at the 1, 2 element, and we're going to have cosine times sine plus negative sine times cosine. So we'd have cosine minus cosine. Well, those go to 0. So we'll get a 0 here. If we look at the 2, 1 element, we'll have the same thing. We'll have cosine times sine minus cosine times sine goes to 0. And then if we look at the 2, 2 element, we'll have sine times sine plus cosine times cosine. So again, we've got cos squared plus sine squared, so that will go to a 1. So we can verify that, and I'll go back and check to see which is the correct version of this, and update the notes before I post them. Okay, permutation matrix. We've seen that a matrix that does a permutation is easy to invert. All we have to do is transpose it, and we get its inverse. So here's one permutation matrix. And remember, all we do to get a permutation matrix is take the identity matrix and reorder its rows. So we've done that here. All we've done is move the third row up to be the first row and move the other two down. And clearly these are orthogonal to each other. If you check the columns, you have just a 1 in one position, in a single position, and each column has that 1 in a different position. So the inner product between any two distinct columns will be 0. And clearly the length is 1, since there's only a single 1 and the rest is zeros. And then you can check that if you do P transpose P, which again looks like we got that screwed up here. So we'll have to check that. But we could also do P times P transpose. But really this should be, these two should be interchanged. And again, I'll fix that in the notes. We get the identity matrix, but it doesn't matter which way you do it. P transpose P, P times P transpose. In this case, both will give you the identity matrix. So here's another example, and we give you a Q matrix, and we ask, is this, even though we've called it Q, is it really an orthogonal matrix? And so I'll give you a minute if you want to pause the video, think about that without looking at your notes, and then come back and check it out. Well, it turns out that this is not quite an orthogonal matrix. Remember, orthogonal matrix is really misnamed, should be called orthonormal matrix, my opinion, and many other people agree. But it's that's a nit to pick. So the columns are orthogonal, but they're not orthonormal. If we look at each column, we can see that if we find the norm of that, we can see that it's not equal to 1. So what is the length of each column? So if you want to pause the video and try to calculate that yourself, and then come back. So the length is actually square root of 2, because we would take 1 squared plus 1 squared square root of that, So that gives us square root of 2. Over here we would have 1 squared plus negative 1 squared. Also gives us 2. Take the square root of that, and we get square root of 2. So if we divide each column by square root of 2, the columns will have unit length, and then it will be an orthogonal matrix. And we can accomplish that since each original column had the same length, we can just put a single 1 over square root of 2 out in front and accomplish that. Okay, reflection matrix is something that's interesting. So if U is any unit vector, all we have to do is form this. So we take U times U transpose, multiply by 2, and subtract that resulting matrix from the identity matrix. And this will actually be a symmetric matrix, which is why this will be equal to Q transpose or Q. Those are both exactly, I guess I should say, and Q. And so if we look at Q transpose times Q, we can work out what that ends up giving us. We just apply rules for transpose to that, work it all out, and we can see that a bunch of stuff ends up canceling. Remember that these are unit vectors, so that's equal to 1, that's equal to 1, that's equal to 1. Well, let's see. No, it's not actually. Something doesn't seem right here. Again, I'll have to check that. I apologize here. I will double check that and see how that's working. Yeah, I'll have to double check that. But the point is that I know that the result is Q transpose Q is equal to I. That definitely holds. I'm just having a little hard time seeing how we get there, how all those things cancel out. But the point is that if you reflect twice, remember Q transpose and Q are equal to each other. So this is like applying Q twice. So if we reflect through a mirror and then reflect back through that mirror, we get back the original. So that's why this has to be equal to I. So U times U transpose is a matrix. U transpose U is a number. That's why I'm thinking that at least one of these up here needs to turn into U transpose U. Although I guess maybe we could, maybe it is right. Let's just take a quick gander here. All right, so this is what I'm thinking. This might actually be right. I'm not going to spend the time to think it through, but if it's right, here's what happens. We group them this way, so U transpose U becomes 1, and then, so then with that 1, we get a U times U transpose, so we get a 4U times U transpose, a 4U times U transpose, so those cancel and we're left with the identity matrix. So that works out, and let me just quickly double check to see if that's what we would actually get. Well, remember those are exactly equal to each other, so we would take this times itself. So we would get let me just write that out here. Maybe this will benefit you to see somebody actually working stuff out live here. All right, so we'll have I times I gives us that. We'll have minus 2U transpose times a minus 2U transpose, so that will give us a plus 4. And so that's a UUT times a UUT, so that gives us that term. And then our inside terms, we're going to have identity matrix times negative UU transpose. And we'll have a negative 2 times, so those combine to that. Okay, so yes, this is all correct. And the key, which I hadn't thought through before I started lecturing here, the key is that when you get to this point, you have to warp your mind and think about other ways to combine these. And so we can combine that in the middle, that part in the middle, and that becomes 1. So this reminds me of when I was in grad school. I took a graduate math class from this crazy Romanian professor. He was really a blast. And he would come in with no notes, no book. He would just come in and ask us, where were we last time? We would tell him, and then he would just, off the top of his head, go through every theorem that was in the book in the exact order that the book was covering it. But his proofs were never like what was in the book. And he would often end up making what appeared to be mistakes. So when you're doing a proof, it's like solving a puzzle. So think about, solving a puzzle like Rubik's Cube or something like that. You don't just perfectly go from your starting point to the ending point without kind of making some errors and realizing, oh, I need to back up. So that's how he would do these proofs. He would start proving something, and maybe we were trying to show that one thing was less than another, and so he would bound one thing and then show that bound, oh crap, it doesn't quite go down far enough, and then he would say, oh, so back here is where I made this bound, and it wasn't quite tight enough, so I better fix that. And a lot of the students complained, saying, geez, why doesn't he just bring in a nice finished proof? But I loved that because I got to see how he thought through even seeming, bad choices of paths. But my hunch is that he probably could have done it perfectly from memory. But I'm guessing that he purposely showed us how one less skilled might actually, stumble here and there. Anyway, I'd like to think that, and maybe that's what I just did here, but no, I was confused for a moment. So, all right, reflection matrices. They are symmetric and orthogonal. So let's take a look at an example. So, or a couple examples. So we choose any unit vector. So here's one unit vector. It's pretty clear that it's a unit vector. Here's another vector. If you calculate its norm, you'll see that its norm is equal to 1. And you should get used to seeing these kinds of things for R2. Square root of 2 will play a big role in normalizing these kinds of vectors. Not always, but this 1 over square root of 2 and negative 1 over square root of 2, or 1 over 2 square root of 2 and plus 1 over square root of 2, those vectors show up a lot. So you should be able to just see those and go, yeah, that's a orthogonal vector, or I'm sorry, a unit vector. Notice that this has two equal magnitude elements. So this is going to point at some multiple of 45 degrees. So if we form Q1, we get something that looks like that. If we form Q2, we get something that looks like that. And here's a follow-up on that. So just reiterating the two vectors that we chose. And so this Q1 will reflect x0 across the y-axis to minus x0. So it reflects anything. It doesn't have to have a 0 here. It'll reflect anything so that its first element just gets negated. That's all it does. So we're showing that xy goes into negative xy. The second one that we had reflects across the 45 degree line because this is a 45 degree vector, so it really points down like this. So that will basically take something that points over here and make it point up here. But anything, so if I had something that was here, it will reflect it and make it over there. So we can think about this 45 degree line that's orthogonal to the vector that we used to create it. it'll reflect along that. So I'll leave this as an open question, and again, I'm seeing, a negative sign up here. So I'm thinking that this actually, well, I'll have to check this and make sure that whether this is a rotation matrix or a reflection matrix. So there seems to be some typos in here on negative signs. So that's actually claiming to be a rotation matrix, not a reflection matrix. And I think that is supposed to be the case here. So all that's saying is that we pick a value of theta and it will rotate by that amount. Remember, the I and the J here are the unit vectors along the two standard axes. So one thing to ask is, does this operation of multiplying by an orthogonal matrix preserve the length of a vector? So rotation certainly does. Reflection certainly does. There's one example of a reflection. Permutation certainly retains the length of the vector, because all it's doing is reordering the elements. And in general, multiplication by any orthogonal matrix will actually preserve the length of a vector. And that's one of the most important characteristics of orthogonal matrices and why they show up inside things like signal processing and communications and things like that. So believe it or not, every time you encode a JPEG image, you are actually taking advantage of some form of orthogonal matrix. So these things are embedded in lots of algorithms that you guys use all the time. Similarly, when you actually do an MP3 encoding, it's a little harder to see it in the algorithm, but there is actually orthogonal matrix ideas embedded in there, although it may not be as obvious. So there's tons of places, not just in compression where you're compressing an image or you're compressing audio, but all sorts of applications take advantage of properties of orthogonal matrices, and one of the most important is that it maintains the length of a vector. So if Q has orthonormal columns, it leaves the lengths unchanged. So the norm after application of Q is the same as the norm before. And this is also important, preserves dot products. So if I take X and Y and I look at their inner product, and then I look at QX and QY, so I transform each of them by multiplying them each by the same Q matrix. It has to be the same Q matrix. Then I take the inner product between the two transformed vectors. It'll be equal to the original inner product. So think about that. What that's saying is that an orthogonal matrix does nothing more. It doesn't change the geometry of the space. So you can apply it to all the vectors in a given space, and really all it does is just kind of moves them all around as a solid whole. Lengths aren't changed, angles between corresponding vectors aren't changed. So it's really, any orthogonal matrix is, all it's really doing is kind of some sort of glorified rotation in some sense of the space. Now obviously, reflections and permutations aren't quite rotations, but it's basically manipulating the space in a way that everything, all the geometry stays the same. And that's kind of the cool thing about them. So we'll talk here about some benefits, certainly not all of them, but the key thing that we can see here is that we end up needing, in a lot of things, like we saw for least squares and doing projections, the matrix A transpose A If instead we could replace A transpose A with Q matrices that are orthogonal, so Q transpose times Q, well, then instead of having A transpose A, we would have this out in front. But remember, that's equal to the identity matrix. So that's why we've left a blank here. Then over on the other side, we would just have Q transpose times B. And so now our act of finding the coefficients for projection, solving the normal equation, becomes very, very easy. We don't even have to do anything to solve it. We just really just take B and multiply it by Q transpose. That's hardly anything compared to having to invert A transpose A. And our projection becomes very simple. So if we take this result and plug it in here, ordinarily we would have all of this machinery, which involves an inverse, which is numerically expensive. Excuse me. If we look at what we get now, it'll be just Q times X hat. So that's equivalent to just Q transpose times B. And so again, no inverse needed. So if you're thinking that, well, what's the big deal? I've got a computer to do the inverse. Well, the pain you feel when you try to do an inverse by hand, the computer feels that as well. It just doesn't tell you about it. So doing inverses take a lot of computations. They're expensive compared to other types of computations. And if we can avoid having to do an inverse, that means we'll be saving a lot of resources. So we can use a smaller processor, or with the same processor, we can do more stuff. And so as engineers, that's what we care about. Our projection matrix then, if we replace all the A's by Q's, we would notice that this term becomes the identity matrix, and so it goes away. So our projection matrix becomes very simple. And we can see that up here, our projection matrix was sitting right there. It's just Q times Q transpose. And we can interpret this another way. When we look at this result up here, Q transpose B, if we write out what that looks like, there's that. Here's our Q matrix. Here's our Q transpose times B. You can see how we've already put the B in doing an inner product with each of the rows of Q transpose. And so now this number here, because that does end up being just a number once we've done that inner product, gets multiplied by this vector, and that gives us this form. Remember, this is a scalar here. This scalar times this vector goes here, and so on all the way out. And so what we're doing here is we're seeing that we can write this projection, which we have over here. Remember, this is equal to little p, the projection. We write the projection as a weighted sum, a linear combination of the orthonormal actually, column vectors, where the numbers that form the linear combination coefficients are just the inner product of B with each one of the orthonormal vectors. A big important idea. So these coefficients are just inner products of B with orthogonal columns, Q sub I. And that is a huge idea. I know it may not seem that big of a deal to you right now, but that is just scattered throughout so many important results in electrical and computer engineering. So I've just rewritten that result up here, and now we're asking, so suppose Q is square and M is equal to N. So in this case, we're less interpreting it as projection and more interpreting it as just kind of finding a new basis. It's almost like changing to a new set of axes, so to speak. So we started off with our regular set of axes, which were the I, J, K, and so forth, the standard basis, and now we're rotating to a new set of orthogonal bases. It's like a rotation of the whole axis, or the whole place, the whole space. And so in that case, x hat is equal to q transpose b. That's the same as x is equal to q inverse b for this case. And basically what we're doing is projecting b onto the whole space. And that just becomes b itself. But the important thing is that what we're really doing here is, what's important is not that the sum of these things gives us back b, although that is important. What we use most in electrical and computer engineering problems is the idea that instead of representing this by the elements inside b, we can represent it with these numbers, this set of numbers. So if we have 100 numbers in here, we'll have 100 of these, and it's just a new way of representing something. And I know you're sitting there thinking like, ho hum, this is so boring, I don't get it. Why is that important? At this point in your career, I cannot adequately explain why this is so important, but just trust me, expanding things out in terms of orthonormal bases like this takes up a huge amount of the material in advanced graduate courses in things like communication systems, signal processing, machine learning, a lot of information theory, secure information security, and things like that. A lot of the key ideas are all based upon saying, well, we start with a vector b, which represents some sequence of information, and we're going to expand that out. Instead of the numbers here, we're going to transform it into this set of numbers. And we do that because that new set of numbers is either A, easier for us to do what we want to do with it, or B, allows us to see some sort of pattern or characteristic that we couldn't see before. And we'll see some examples of this later on in the course when we get more into the application ideas. So for now, just trust me. Expanding in terms of a set of orthonormal basis vectors is extremely important. And so here I'm just giving you kind of a teaser to give you an idea of how big an idea this is. So the book says that hey, this equation here that I've rewritten here, it's a seems not worth mentioning type of equation. But it's really the foundation of something called Fourier Series and a bunch of things related to that. And there's a bunch of things that are called transforms that come out of various subfields of ECE and other related fields. So like in physics and applied math, things like that. These ideas are huge. And the basic idea is we start with some vector b that represents the signal or information that we're given and that we've kind of quote-unquote received. And then we have a set of orthonormal vectors. That's the q1 through qn. And what we do is we compute the inner product of our given b with each of the orthogonal vectors, and we get a series of numbers. And that new series of numbers we can use in place of this sequence of numbers. Why can we use them in place of? Because given this new sequence, I can use the right-hand side to get back to the old sequence. Okay, fair enough. But why do that? Well, it turns out that operating on the new sequence of numbers, so if I take where'd my pointer go? There we go. So if I take this number all the way out to this number, if I take that set of numbers, something that I want to try to do from an electrical and computer engineering point of view will be easier to do, or maybe only possible to do in that quote-unquote new domain. And then I can do that So I can modify these numbers in some way, and then I can still use this formula with the same Q1 through Qn, but with the inner product numbers slightly changed because I wanted to change them. Add them all up and I'll get a slightly different vector, which has done to it something that was important to me. So maybe I used that to reduce the amount of noise in my original signal. We talked about the curse of noise. Or maybe I did something else to it. So this idea right here, summarized right here, that we take some given vector or function. We can think about doing this to functions as well, but here we'll just focus on doing it to vectors. We break a vector that holds some pieces of information that we're interested in, but not in a format that's useful to us or maximally useful to us. We break it into orthonormal components, so that's this right-hand side. Then, adding the pieces together, we effectively implement the inverse transform, and it puts the function back together again. So this is sort of like Humpty Dumpty. We break Humpty Dumpty apart, and then all the king's horses and all the king's men come along and put it back together again. Now you might think, why on earth would I do that? Break it apart and then put it right back together again. And I alluded to the reason why we do that. We often either A, want to modify these to do something to our original B, to make it more useful to us, or sometimes we never even go back. All we need to do is look at these inner product results and it will allow us to make a decision. So this is simplifying things quite a bit, but the idea is pretty close to reality. Suppose B holds the samples of a speech signal. So somebody utters into a microphone some little phrase, and we just take samples of that wiggling voltage coming out of the microphone, and maybe we sample it, like something like 44,000 times per second. So if you're an audio enthusiast, you'll recognize that I just quoted something pretty close to how fast audio is sampled when put onto a CD. So suppose I take that speech and I sample it at about 44,000 times per second. So every 1 over 44,000 seconds, that's how often. 1 over 44,000, parenthesis, seconds, that's how often I will take a sample of this. So suppose I have a couple thousand elements in my B matrix, or my B vector. I could compute a couple thousand of these, and then I might have very carefully chosen my Q vectors so that looking at those computed inner products, the Q whatever inner product would be, will tell me, I can use those to determine which speaker said that. So, simple case, I might be trying to decide between two, previously known speakers. Is it speaker A or is it speaker B who just said that? And so I can look to see, I can look at those numbers, and it will be easier to deduce from the inner product numbers which speaker said it than it would from the looking directly at the B values. So again, it's kind of hard to explain all of this without some other machinery that you need to know. But I'm just trying to allude to this and maybe get you interested in going on to these other courses. Now here's another example. As I alluded to, every time you create a JPEG image, you're basically doing this idea. Remember, these columns that are orthonormal vectors, we can think of as being in put as columns of an orthogonal matrix. So here's how you would use this, and again, this is just roughly the idea, to create a JPEG image. So you've got some original image that's not compressed, and it's got some number of pixels. So maybe 2,000 pixels by 5,000 pixels or whatever. What we're going to do is break that image down into 8 by 8 pixel blocks. And we'll do these series of steps for each 8 by 8 pixel block. So basically, essentially, we don't quite do it this way, but it's essentially like this. We take each 8 by 8 pixel block and convert it into a vector B. So we just string out those 64 pixel values into a 64 by 1 vector. Then we transform each vector B into these coefficients, and I'm just using a B tilde here. So I take each of some given orthogonal, in fact orthonormal vector, and I do the inner product. And since I would do this for all up to n, and there's 64 elements in my original B, I would do this 64 times. Now, that step is equivalent to taking this original B, which holds the 64 pixels, and just multiplying that B times some appropriate Q transpose matrix. Okay? So Q transpose times B would give me a new vector, which I would call B tilde, and it would have 64 elements. All right, so far in the parlance of signal processing and information theory, I've not changed anything. You give me the B elements, I can find the B tilde elements. You give me the B tilde elements, and I can find the B elements. So I haven't really done much, but I've converted into a new quote-unquote domain, where this transform domain, where these things, where the B tildes live. And if I pick my Q matrix correctly, and for JPEG there's a very special Q matrix that we pick. It's called the DCT, the discrete cosine transform, which is related to the Fourier series. If I pick that, there will be a high probability that lots of the B tilde sub k coefficients after the transform will be small, whereas the original elements might not be small at all. And so that's the key. We pick some special Q matrix such that we have a high probability for usual type pictures that lots of these coefficients will be very, very small. And so we effectively throw away the small BK coefficients. And so somehow now we have a smaller number of coefficients that are significant. So to just put this in perspective, we've got 64 coefficients here. We've got 64 elements here. We've got 64 coefficients, but they can be viewed as elements in a B tilde vector. We've got 64 of them. All 64 elements of the B vector might be significant numbers. I can't really throw any of them away and expect very little change to the image. But over here, maybe only 6 to 10 of those 64 coefficients will be large, and all the rest will be really small. Small enough that if I threw them away, I'd hardly be changing the nature of the B tilde matrix or vector. And more importantly, when I transform them back into the equivalent of the B, now it's not going to be the same B because I threw away some of the small ones, but it'll be damn close to the original B. So close that your eye won't even really be able to tell. And so here's the key. Throwing them away doesn't just by itself doesn't help us reduce the amount of data that we have to store, but the remaining ones that are not small, which is going to be some small number of these, I need to somehow efficiently code those so that the decoder knows their values, or at least a close approximation to their values, but also kind of knows which of them they were, right? Because if I've just thrown away a bunch of the small ones, I kind of need to keep track of the remaining 10 coefficients. Where were they in the indexing scheme here. So there needs to be some clever way to do that. And there is. And every time you take a picture in your camera and it automatically converts it into JPEG, this is being done over and over and over. And it's all based upon this idea that we can expand some given vector in terms of a bunch of orthonormal vectors where the coefficients are just inner products, and exploiting the ideas that we talked about earlier, that this maintains norms and maintains inner products. So by that I mean, let me get rid of the ink here. By that I mean, if I were to look at this B tilde vector, all 64 elements stacked, the norm of that B tilde vector would be the same as the norm of this B vector. And then after I've thrown away the small coefficients, because they were so small, the resulting norm after having thrown away all this stuff will be approximately the same as the norm of this. And that's all because of this orthogonal transform bit. So that's about all I can, kind of summarize at this point. But this is actually very interesting stuff. And if you really are interested in how data compression works and how images get compressed and how audio gets compressed, this is the machinery that you need to know, and you're learning about it here. If, on the other hand, you're just approaching this course like, just tell me what's going to be on the frickin' exam and let me take the exam, not necessarily the best approach. But if that's your approach, then you don't need to know any of this. But boy, that would really be a pretty sad approach to this course, to say, I only care about what I need to know to pass this particular exam, and I don't care what I'll need to know when I become a real engineer. Okay, enough philosophizing and chastising. I'm just going to think that you're out there saying this is all really cool stuff, and I'm looking forward to how it fits into the grander scheme. All right, let's look at an example, see how this really works. This is a stupid textbook example. Gives you no idea of how things really work in the real world, but it shows you the mechanism so that you can verify that on the exam you can go through the motions and figure this crap out. All right, so we've got some matrix Q. We've got a normalizing constant out in front. You can check that all these columns, including the 1/3, have unit length, and that all the columns are orthogonal to each other. So suppose we have a vector B, and we do all the separate projections onto the Q's, and we call those projections the P1, P2, and P3. So P1 is going to be this inner product times Q1. So if you do that inner product, you will find that it turns out to be 2/3. So we take the number 2/3 times Q1. Then P2, we would find is also 2/3, but times Q2. And then P3 will be negative 1/3 times Q3. And so now, instead of representing B this way, we can represent it in terms of these numbers. 2/3, 2/3, negative 1/3. So if we were to actually take those numbers, put them into a vector, and then multiply that vector times Q, so all these things go into there, we would actually see that that results in the vector B. That's really what this equation with all of this stuff here is actually doing. And so numerically it evaluates to all this, and then you add all that up, and wow, you get back B. So that's the mechanism of it. Now, hidden in this problem is something that's actually backwards from how we would really use it. Notice that our original B in this case is pretty sparse. So we end up with something that has 2 zeros and just one non-zero value. And we've transformed that into a vector that has values that are, kind of all over the place, 2/3, 2/3, and -1/3, and are not necessarily small in the context of this. So in most ECE applications, this is the reverse of what we normally want. So I thought about revising this example to have it go the other way, but I didn't. I was a little pressed for time and didn't do that. But in reality, we would want to start with a vector here that is, kind of fully populated, and showing that when we break it down into this, we might end up with only one significant one and maybe one kind of small and one kind of zero, which means that we could approximate B with just one coefficient times Q1 in the case where this one was significant, this was really small, and this was zero. So this idea of taking some vector B, expanding it out in terms of an orthonormal basis, and seeing that, I really only need one number to approximately represent it. That's the essence of data compression, at least a certain category of data compression, like JPEG and MP3 and things like that. But that idea is also embedded in lots of other ECE type stuff. Okay, let's get on to Gramschmidt process. This is the second part of this. So we've already talked about how orthogonality makes it easy to do projections. We just saw that. Now we want to know, how do we actually construct orthogonal vectors? So if we're given a bunch of vectors that span a subspace and I want to project onto that subspace, those vectors, those given vectors, may not be orthogonal. But if I can find an equivalent set of orthogonal vectors that span the same subspace, I can replace my given vectors with this new set, and because they're orthogonal, the process of projecting will be that much easier. So we've looked previously at an LU decomposition. You give me an A matrix and I can decompose it into L times U, where L was lower triangular and U was upper triangular. Well, now we want to make at least one of these matrices have an orthogonal columns. So the Gramschmidt process is related to that. And so what we'll end up doing is we'll end up getting A is equal to some matrix Q that will hold the orthogonal vectors, actually orthonormal vectors, and then some other matrix R, which will be whatever's needed to combine the Q columns into the A matrix. So let's start off trying to understand how to do this in the classic style of how this book works and how I like to lecture. That's one of the reasons I like this book. Let's just sneak up on this and see how it works from a simple illustration rather than laying out all the heavy-duty theory first and then seeing some simple things. So we sneak up on it with a simple development, and then from that, without any proof, just say, bam, this is the full picture for it. So our goal is to find some orthogonal vectors. Now, I know that we've been using uppercase for matrices, but for this little section here, the capital A and the capital B are going to be vectors. So we've been given some original vectors that are not orthogonal. We'd like to find two new vectors that are orthogonal, such that the span of the original vectors is the same as the span of the orthogonal vectors. That's what we would like to do. So once we find orthogonal vectors that do what we want, then I can make them orthonormal by just normalizing them. So it'll be a two-step process. So there's how I would make them normalized, and then we rename them with lowercase things. So that's a little bit better. So suppose I start off with two vectors, A and B, and what I want to do is find two orthogonal vectors, capital A and B, such that they have the same span as the original vectors A, B. So if this screen is the plane in which A, B lie, I want two vectors. Well, I can pick that one. In fact, I can pick it equal to A. So there, I've got the A contribution covered. And so now I just need some vector that kind of points orthogonal to A, but lies in the same plane. So the span of those two things, so this one down here would be capital A, which is the same as little a, and then this vector up here would be capital B. So those have the same span as the two original little a, little b, but they are orthogonal to each other. And then I can normalize them. But we want to mechanize this. I mean, it's easy to see it on page and draw it, but we want to be able to mechanize how do we do this without having to draw any pictures. And more importantly, how do we get a computer algorithm to go through and do this? So as I said, we're going to assume we can always do this. Just pick one of the given vectors as one of our new vectors. And then we need to find the capital B vector. And so the approach comes out of our least squares idea. Remember, if we think about projecting B onto big A or little a, doesn't really matter what we say, but let's say big A, projecting it onto big A, we project down like this. And then remember, if we ended up finding the vector here that was just the difference between B and its projection, we saw that that vector was going to be orthogonal to the original. That was kind of the whole point of how we derived least squares. And so B minus its projection onto A will be orthogonal. And we know how to find the projection of B onto A. We've been down that road. Remember, capital A here is a vector, not a matrix like you're used to seeing. So that's why down here we can put this in the denominator because that's actually a scalar. So our first Gramschmidt step, Gramschmidt, just the name of the two guys who came up with this idea. I don't know if they worked together or individually, probably individually. And they probably both came up with this, or maybe one came up with part of it and then another one made it a little bit better or whatever. So here's our first step. Capital B is just little b, and then we subtract off the projection of little b onto big A. And that's it. And we can check to see that B is perpendicular to A. That's easy enough to do. We can do the inner product between A transpose or between A and B. Remember, capital B are both vectors here. And so if we multiply this through, and remember this whole thing is just a scalar, so we can take this A transpose all the way through to there, and so now we get A transpose A here divided by A transpose A. Those cancel each other, and we're left with A transpose B minus A transpose B, which gives us 0. So yes, indeed, we can verify that this process does give us something that's orthogonal, but we knew that already from how we set this up. But it's always nice to just kind of double check. So we started with two vectors, and we picked one to start off. We picked little a to be big A, and then we found big B to be orthogonal to big A. What happens if we've got a third vector? What do we do? And notice that we're kind of adding this in. Suppose we've already done that first step. So we've got capital A, we've got capital B. Now we get some third vector that's thrown our way. And presumably it's sticking up out of the plane spanned by A and B. So we've got a third direction with some vector C. And now we want to find a third orthogonal vector that will be orthogonal to big A and big B. So let's recall how we got big B. So we have our big A here, we have our little b here, we projected it down, and then we did the subtraction of B and P gave us the vector big B. So we can do the same thing. We can take and find the projection, subtract off the projection. So there is the negative of the projection. And notice that because capital A and capital B are orthogonal, these terms were very easy to calculate. We already saw that to project onto a set of orthogonal vectors is easy. We just do an inner product essentially with each of the vectors. And so that's what we're doing. And so that's why I say here easy projections. And that's because the A and B are orthogonal to each other. And so over here we've got our plane spanned by our A and B, which we've previously found. We get some new C. We project that down onto this plane, and so the sum of those two components, without the negative signs, just adding them up instead, will end up giving me something that sits right there. So that'll be the projection onto A, which might come out to there, the projection onto B, which might come out to there, and then if we look at, well, I didn't draw that very well. Let me try that again. Let me just extend this. And so we've got this, and we've got this. And this is actually a right angle here, remember. So we've got the projection of C onto B, the projection of C onto A. That's these two things. We add them together, that's this, to get this projection. And then we subtract it from C to little c to get this resulting vector. So the subtraction accounts for the negative signs there. So that's what we do. And the key here is that it's very easy to do these projections because A and B, capital A and B, are already orthogonal to each other. So this is the key idea. Every new vector that you get, assuming it sticks out of the plane or the subspace you've already dealt with, you just subtract from it its projections in all the orthogonal directions already figured out. And then once we end up, if this is as far as we want to go, we now can just normalize all these. So we take our A and we normalize it, we take our B and normalize it, we take our C and normalize it. And now we've got three orthogonal unit vectors. And it's a little hard to see in the picture, but all of these angles are right angles to each other. So we've got three unit vectors that are orthogonal to each other, but they're not necessarily aligned with our original unit vectors, which would be the 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, those would be our standard axis vectors. We've got a new set of axis vectors that might be tilted and rotated with respect to the original. And that's kind of the key idea here. So here's an example. Here's our original A, B, and C spanning some subspace. We set our big A, remember vector, equal to the original given A. And we do our process. So we just calculate this projection coefficient. And so for this case, that just ends up being 2 over 2 times our original A subtracted from B, and we get this result. And then we go through and we find our C. And so now we have, after normalization, we would find the norm of this and divide by it, the norm of that vector and divide by it, the norm of this vector and divide by it, and we get our 3 orthonormal vectors. And so let's re-envision what we just did. We'll rely on this ABC notation and Q1, Q2, Q3. So there's no reason why we have to stop at 3 vectors. If we're in a higher dimensional space, we can start off with however many vectors as the space allows us to have that are linearly independent. So our assumption was that the given vectors were linearly independent. And so however many of them there are, we end up with that many orthogonal, in fact, orthonormal vectors. But we're going to view the original ones as columns of some matrix A, and we're going to view the new ones as columns of some matrix Q. And so here's the idea. Since we have an A matrix and a Q matrix, and their column space now is identical, there must be some matrix that connects them so that I can convert Q into A and I can convert A into Q. And we call that third matrix R, and we hypothesize that there should be some matrix R that when I multiply Q times R in that order, I end up getting the matrix A. And I explain, I show explicitly here what that R matrix is going to be. So here's our A matrix with the columns A, B, C, and this is just showing it for the 3-dimensional case, but we can do it for however many vectors we want. Here's our new vectors Q, sitting in the columns of the Q matrix, and then here's what R would look like. And we can see that this element, this first element of the R matrix, will just be Q1, which we computed here, inner product with A, so it's the angle between those, and that's what goes in there, and then the remaining elements are 0. Okay? Then we look at B, inner product with each of the first 2. Remember, B was the second vector that was provided to us, and then zeros underneath that. And then for the third vector, it actually interacts with all 3 of the Q orthonormal vectors. Now, remember, since A was what we started with, and we made sure that B, the resulting Q2 and Q3 were orthogonal to A, we could really say that what we're really doing is each one of these elements here is always all the inner products, right? So let's look at the structure here. Let me clear this off. I'll try to say this slowly so that if you want to write it down, you can write it down. But we would have Q1 inner product with A, Q2 inner product with A, Q3 inner product with A, Q1 with B, Q2 with B, Q3 with B, Q1 with C, Q2 with C, Q3 with C. But remember, Q2 with A is going to be 0 because Q2 is orthogonal to A. And Q3 inner product with A will also be 0. So really the elements in this R matrix are just all these inner products, but some of them we know ahead of time are going to be 0. So that's one way to view that. But another way to view this, why is R upper triangular? Why does it end up that way? Another view, well, every step, A, B, C are combinations of the Q1, Q2, and Q3, but the key is that the later Qs are not involved in the earlier computations. Earlier meaning, computing Q1, so Q3 is not involved in computing Q1. Q2 is not involved in computing Q1. And so that's kind of why we need this this way. So if we look at this to compute A, it's going to be really A will be the linear combination of these three columns with these as the weights. So I can build A just with that number because Q1 and A lie collinear with each other. Now I want to compute B. Well, remember, B was in the space that both Q1 and Q2 span. So it's somewhere, it lies somewhere so that it interacts with both Q1 and Q2, but Q3 is orthogonal to that subspace. So we end up with the 0 down here. So this is a very important structure. The Q matrix is an orthonormal matrix because we've normalized it, and the R matrix is upper triangular. So here's an example. I don't show you how to go from the A's to the B's, or I'm sorry, from the ABCs to the Q1, Q2, Q3, but I think this is the example we looked at earlier. Let's just take a quick zip back. Yeah, that looks like the example that we already did. So we already figured out how to get to the Q1, Q2, and Q3, and here all we're doing is interpreting the result in terms of the QR factorization. So here's the Q matrix. So we're literally just taking all of these elements and putting them in there. And then here's the R matrix, and we can find these numbers by doing all those inner products. So this is going to be Q1 inner product with A. So we would do the inner product between these two. This number here will be Q1 inner product with B. This number, the square root of 6, will be Q2 inner product with B, and then a 0 because B will be orthogonal to Q3, and you can check that. And then the last column will just be A with Q3, A with Q1, A with Q2. I'm sorry, C with Q1, C with Q2, and C with Q3 will give you those three numbers. So there's our decomposition QR. And notice that the things down the diagonal there, let me clear some of this stuff out here. The numbers down the diagonal here are the lengths of our A, B, and C. So they are these things. So we already have those things worked out. Now this QR decomposition, looks a little less beautiful, quote unquote, than the LU decomposition, only because the LU had this nice structure where the L was lower triangular and the U was upper triangular, so you had that kind of symmetry in some sense going on. But here, the fact that Q is an orthogonal matrix is huge. That's a powerful idea. And it's absolutely central to numerical linear algebra. So the LU is nice, but the QR does a lot of the same things, but it ends up doing them in a way that is better suited to numerical calculations. We're not going to go into the details of why, but you should just kind of be aware that the QR is a powerful thing that is really widely used when trying to implement all these things on a computer. So let's just finish this set of notes off here with looking at why would this QR be useful in least squares? That's kind of how we started things off, talking about some of these ideas in this set of notes. So let's look at our A transpose A, which we know plays a fundamental role in our least squares. And so if we can replace each A by QR, to get the A transpose, we're going to need to transpose each of those, and then interchange their order. So we'll get R transpose Q transpose times A, which is QR. But we already know that Q transpose Q gives us the identity matrix, so we don't even have to write that. So A transpose A gets replaced by R transpose R. And so then the least squares equations become something that looks like this. And then when we solve this, we can actually solve this equation by, the r, actually r ends up being square and ends up being invertible. So we can actually multiply by r transpose inverse to get rid of that, then multiply by r inverse to break free x hat, and so we end up having this as our solution. So we end up with an orthogonal matrix that we transpose and multiply by b. We do still need to do, at least in principle, an inverse. And you may be saying, hey, wait, I thought we started off saying that like Q matrices were so important that if we could get ourselves into that format that we wouldn't have to do any inverses. But here's the key. We don't really find the inverse of this if we were doing this numerically, nor actually even by hand. The key thing is that R has upper triangular form. So since R has triangular form, you wouldn't actually compute the inverse of R. You would just solve this by back substitution. So since R is triangular, there's going to be one equation that has just one unknown that can be easily solved. Then you back substitute that solution into the next one, which originally had two unknowns but now has one, and you can solve that. Now you have two knowns substituted into the equation that has three unknowns to reduce it to just one unknown, solve that, and so on and so on and so on. So the point of this is that from a computer's point of view, and actually from a hand point of view, if you've already got the RQ decomposition available, solving the least squares problem is extremely easy. But from a computer point of view, even counting in the cost of doing the QR decomposition and then solving the least squares problem with back substitution, you're still far ahead compared to forming A transpose A and doing the inverse of that. So this becomes a very computationally efficient and fast way to solve the least squares problem. And it has very good so-called numerical properties. So it handles issues of round-off errors very well, and so on. So it really is one of the preferred ways of solving the least squares problem. All right, we'll stop there, and I'll see you in the next video, which I promise you is in a new chapter, chapter 5.